So hello, my talk is going to be a report about benchmarking that we have done on our fairly new SGI UV 300 system with 12 NVMe SSD PCIe cards from Intel. PCIe NVMe cards are getting more and more popular, as we all know. But the reason that people are really investing them is random access. It's IOPS. IOPS is what drives innovation in this sector, the SSD sector, and that's why people are willing to invest there. We're taking a little bit of a different approach here. Because we think that not only random access, this equipment doesn't benefit applications that require random access performance, but throughput performance also can be exploited and and there are several applications that can benefit from their sequential throughput performance. So the opportunity for this benchmarking is naturally in-memory databases, which is a technology that our researchers got interested in after we acquired the SGI UV 300, which, by the way, has 12 terabytes of RAM. On this particular example, we had a financial database that required getting in and out between terabytes and petabytes of data. The question is, right, you have your in-memory database and there's a good performance there, but how do you really load it and how do you really save it in a decent amount of time? How do you recover from failures when the system or the application crashes? How much time to go back in business? This is a great opportunity to exploit the benefit of PCIe NVMe SSD storage, and this is how we got into this project, as I said. A few words about our system. Our SGI UV 300 is called Appel, and it's a 12 terabyte RAM and 384 Ivy Bridge core system. On that, we have 12 Intel DCP-3700 cards. As you see there, this is the map of the PCIe slots on Appel. There are 96 available PCIe slots on that machine. We filled in 12. I think that SGI on supercomputing has gone up to 64 on this particular machine. So the question here is, all right, I'm able to have a single Linux system, a single kernel, not with one or two, but 12 SSD cards. How do I organize this in the best way? How do I get the most value of these cards? And how do I expose them to the application? Do I format them individually and mount them and give them to the application? Do I put a volume manager on top of them? Or even a parallel file system, Lustre or GPFS? What really gets me the best performance there? So the software that is running in that system is is on this slide, and I think the most interesting part, of course, is the NVMe driver. This is an SGI optimized NVMe driver that allows for an optimal distribution of the I/O submission and completion queues throughout the system, so that there's at least one queue per socket and one interrupt. So basically, we keep the data in L3 cache, and we avoid context switches and NUMA transfers. The system is running /11 SP3. There's a workload manager through which we submit the benchmarks, PBS Pro. These are technologies that we generally use at our HPC center. We use Linux software RAID. Who doesn't? We use XVM, SGI's NUMA-aware volume manager. We use the XFS file system, and we also use GPFS. So we were familiar with these technologies, and we wanted to try which one basically would give us the best performance for this project. The way that we market is as follows. As I said, we're interested in streaming throughput performance. We don't do IOPS testing on this one. Using a variety of volume and file systems. First of all, we establish a baseline. Take one of the cards, we add it with XFS, and we mark that. At the next stage, we are assembling volumes either with Linux software RAID or with XVM. Of course, we format them with the file system, in this case XFS, or GPFS. GPFS, of course, it doesn't require a volume manager. It does striping on the file system level. We use, as a benchmarking tool, we use IOR, typically used in national labs, in procurements, and very well known. I'm mentioning here a number of options. Not precise, because that's one option that we experimented with. We also use direct I/O. That's the suggestion both from SGI and Intel. Basically, we played also with the number of the MPI threads. A few tuning notes here. On the first part, that's just the script that distributes IRQs throughout the system in accordance with the hints that the SGI modified NVMe driver has provided. We also disable C1E power states. I also mentioned that the system has hyperthreading disabled. Before each test, we wipe the cards using block discard, and we make a run of each test that we just throw away. This is just for conditioning the SSD before we do the actual run, and we record those numbers. So this is the baseline. We format the Intel card with XFS, and we mount it. I don't have here the no barrier and no access time options, but we also used those. Basically, what we saw was that we were able to achieve the spec sheet numbers on read and write speeds using 6 IOR threads, which is pretty good. With these baseline, we go ahead and we expand the test to 12 cards. Now, this is one of the options that I mentioned before. You have 12 cards. Each of them is not too small of a file system. It has 2 terabytes, so you could probably format and mount them individually if your application really can take advantage of that. That particular database actually is able to go through physical mount points. You can have as many as you want, so it didn't actually care if we mounted those file systems individually or if we striped them over XVM. It didn't make sense to do this experiment. And IOR is perfectly capable of conducting this test. In this case, we got the best write result for 24 gigabytes per second using 132 threads, and the best read result for 32, that was 32 gigabytes per second using 132 threads. Let me just explain a little bit more what we're doing here, because this is part of the benchmark methodology. So we ran IOR using multiple transfer sizes, starting from 1 megabyte transfer size and ending up at 16 megabytes of a transfer size. So each chunk of data that IOR was throwing down the block subsystem drain was this big. We repeated all these tests for 33, 66, 99, 132, and 264 IOR threads. So this is what we got. Obviously, larger transfer sizes favor sequential throughput, as we all know, because there's less overhead in the operating system and on the hardware to do gather operations and transfer the data this way. Also, let's say that the large number of threads sort of raises the queue depth equivalent, if I'm allowed to say that, which means that basically it saturates the cards. At the same time, as I'm saying there, we were also keeping a close eye on the IOStat numbers, which reported close to 100% utilization. The next test was with GPFS. GPFS doesn't require a volume manager, and it can address all these cards as individual NSDs, and it's doing the striping on the file system level, of course. We tried 2 options here because most of you will know that the important factor or tunable on a GPFS file system is the block size, and that kind of determines, in the software level, of course, its performance in sequential workloads. So we formatted with the 1 megabyte block size and with the 4 megabyte block size, which is the the next test. This one gave us a fairly good result, 31.6 gigabytes per second with 66 IOR threads. The write result is not so good, I would say. That is at about 18.8 gigabytes per second using 33 threads. Let's compare and contrast the next test, which was with the 4 megabyte block size format. This is slightly better in terms of write speeds. We got 22.4 gigabytes per second using 66 threads, and the read result is still good. The baseline, the read result is pretty good there. The important part here is that these tests were done with GPFS 3.5, and in that version, IBM didn't have that many improvements. Basically, I doubt the file system was NVMe aware. Maybe I'm wrong, but we expect better performance on version 4, which is a test to be done in the near future. This is another test, so we go back to the discussion about the volume managers. We're using Linux software RAID, and we are assembling all the cards on a RAID 0 volume, and we formatted with the XFS file system. We run the same tests with IOR transfer rates from 1 megabyte to 16 megabyte, and from 33 threads to 264. This is a very good read result, 29.8 gigabytes per second, and this is also a very good write result, close to 24 gigabytes per second. IOStat at the same time showed us full saturation of the hardware. These results are pretty good and very nicely, they show very nice scalability compared to the baseline. The same test, but with a slightly different setup in terms of the MD RAID. This is where we use the Intel Rapid Storage Enterprise extensions. I think that's the marketing name. It used to be called IMSM. So this is really RAID 0 volume with an external metadata container. Basically, Intel's IMSM container allows you to define multiple volumes within the same RAID 0 volume in this case. We don't do that anyway. The results are pretty similar, although slightly less consistent on the 132 threads, I think this is pretty much insignificant. So I would say that the results are similar in both cases with empty RAID. This is the same test, but in this case we're not using Linux software RAID. We're using SGI's XVM, which is a NUMA-aware volume manager. I would say that it's pretty good, but not as good as the empty RAID results. Basically, the winner is no RAID. The best performance that you can get out of a collection of these SSDs, of NVMe SSD cards on a single system, is still without putting a virtual device or volume on top of them. Although even though the MD RAID options come pretty close to come second, but pretty close to perfect scalability. Not perfect, but very close. And there is, of course, the exception of the read throughput which is about 9.1% in the Linux software RAID, and the explanation for this is most probably that even though the NVMe driver did a marvelous job in giving us that many submission and completion queues to spread all over the system, what did we do? We went and we put a bottleneck on top of that. We put a virtual device with a single queue, and everything has to go through there. But still, I would say that the numbers are good, keeping this in consideration. And of course, going back to the original issue here, these cards give excellent throughput performance, so they're not only for IOPS. It's probably on the most expensive throughput performance hardware, if you ask me, but they are really, they're really impressive. So with this, I would like to thank both SGI and Intel. People from both companies have helped us with this project. And there is a white paper if you would like to take a closer look in the testing that we have done, with a little bit more information there. And I'm ready for questions.
So thank you. Quick question for you.
Mm-hmm.
Obviously, the question would have crossed your mind as you use these NVMe cards, a trade-off between spending money on memory versus having more of these cards, right? And within the scope of this project, did you see that if you had, let's say, had your UV300 with 6 terabytes of memory and more of these cards, for your set of applications, where would it fall?
We didn't do a cost estimation on this project, really. I don't know, Paul. Would you like to chip in on that?
Comparing the performance of memory on the system for certain data and then actually forcing yourself to use less memory and using more of these cards and see what the performance difference is. Forget about the cost.
We didn't do that. No, we didn't do that. That could be another thing to try. Of course, yes.
Yeah, and I guess to some extent,
Yeah.
the issue is basically the applications you were looking at use as much memory and as much SSDs. So, any other questions?